In this video, I'm going to be going over some series circuits again and also talking about some of the lab assignments you'll be working on and how to set those up. So let's just review really quickly. When we have a series circuit, so for example, we have a power source here. I'll call it V1, and let's say, for example, it's 10 volts. And we have some resistors connected here. Now let's say these are all the same value. So we have, for example, 1 k ohm resistor here, 1 k ohm resistor, and a third 1 k ohm resistor. Now if you remember the steps for how we do some of these calculations, we have some kind of definitive ways that we want to do this in order to, first of all, start with, we want to calculate the current. And also, I'll show you another way we can actually calculate these voltages without calculating the current. But for starters, let's do this. So the first step was finding RT, the total resistance, which is the resistance of all three resistors here. And I'll label these R1, R2, and R3. So as you know before, this is simply the sum of these three. R1 plus R2 plus R3. And it's pretty easy to see quickly here that if we add these three values, it ends up being 3,000 ohms. So that's 3 k ohms. Now to find the current, the second step is we want to find out what the current is, I sub t, and that's going to equal V over R. But we have to be a little bit careful here when we say V over R, which resistor we're looking at. We're going to look at, since the voltage is across all three resistors, the total resistance, we're really saying that it's V1, the source voltage here, divided by RT, the total resistance. We can't just divide it by one of these individual resistors. So if we plug in these numbers here, we have 10 volts divided by 3,000 ohms, and I'm writing it out as 3,000, even though that's not engineering units, but that's the way we'd plug it into the calculator, and that ends up equaling 0.00333, which we can round to, for example, 3.3 milliamps of current. Now, what is kind of interesting here is that if we look at what that number represents, that's really 3.3 times, with a little rounding, 10 to the minus third. The resistor values, though, are in powers of 10 to the third. So what's kind of cool about this is that if we're in the next step, we want to find the voltage across each of these resistors, we don't even have to worry about the units so much in this case, because the 1,000 ohms is 1 times 10 to the third. And if we're trying to calculate, for example, the voltage across R3 here, plus and minus, that ends up equaling 1 times 10 to the third times ohms times 3.3 times 10, to the minus third. And if you remember from your algebra, this ends up, these numbers up here end up canceling, the exponents end up canceling, and we end up with 3.3. Now what did we calculate there? We're calculating the voltage. The voltage across a resistor equals the current flowing through that resistor, I'm going to call it IR, times the resistor value. So in that case, when we multiply that out, we ended up with 3.3 volts. Now, as you might expect, this is going to be the same for each resistor because they all have the same values. Now, what is the total voltage drop across all those resistors? We could write this out as VR1 plus VR2 plus VR3. And if we add those all up together, we end up with 10 volts, 3.3 with this extension here. If we add up those three separate voltages, we end up with 10 volts. And the way I sometimes draw this out, that hopefully is helpful a little bit, is remember this, well, I don't know if I've really explained this in depth before in the class, but the most negative part of the circuit is what is connected to ground, or 0 volts. That's typical with circuits. Now there's some weird exceptions to that. And the symbol that I use there is this, it's the ground symbol that's used for these circuits. I draw like that. Now you may have seen some other symbols for ground. We'll probably talk about those a little bit later on. But one way of looking at this is if we're starting at this point here, let me use this different color here. If we started our 0 volt point here as 0, we can kind of draw like a graph here, 0 volts. When we get up all the way up to this point here, we've increased the potential voltage by 10 volts. So now we've gone up from 0 volts all the way to 10 volts. The voltage drop across each of these resistors is 3.3 volts. So what happens, and I'm going to draw these little plus minuses here. This doesn't show that the resistors have any voltage. They're not generating voltage, but there's voltage dropped across each of these resistors. Clean this up a little bit. And what we're going is we're going from a positive voltage to a positive, and each time we're going to subtract the voltage across each of those resistors. So what ends up happening here is a voltage across the first resistor, second resistor, and third resistor. So I'm going to write this as VR1, VR2, and VR3. And if each one of those is 3.333 volts, as we subtract that, we get back down to our 0 volt level there. This is referred to as Kirchhoff's voltage law. And really what it's explaining is that the input voltage, the sum of all the voltage on the input, is going to equal, or Vn, is going to be equal to the sum of the voltage drops. So we have VR1 plus VR2 plus VR3. And the other way we can write this is that if we subtract 10 volts from those voltage values, we should end up with 0 volts. So we start at 0, go up to 10 here on the top, and then as we're going through each or across each resistor, we're dropping that voltage until we get back down to 0 volts. Okay, let's take a look at a different circuit here. In this case, I'm going to have some different values. So I'm going to have, for example, let's say this is a 400 ohm resistor, and this resistor is let's make this 100 ohms. Call this R2, and the one on the top is R1. Okay? So if we calculate the voltage and current values here, we have 10 volts for our voltage source, V1 equals 10 volts. If we're going to calculate the current flowing through these resistors, I is going to equal V over RT, and RT in this case is simply the sum of these two, 400 ohms plus 100 ohms, so that equals 10 volts divided by 500 ohms. So if we calculate that out, that ends up being 0.02 amps, and we'd write that as 20 milliamps. Now, again, multiplying this value times these resistor values is going to give us the voltage across each of these resistors here. Let's go ahead and do that really quickly. And I'll do that in a different color again. If we take our 20 milliamps, 0.02, times the top resistor, 400 ohms, we end up with 8 volts. And the bottom one, if we take 0.02 times 100 ohms, we end up with 2 volts. And as expected, if we add these two together, we end up with 10 volts. So our source voltage, 10 volts, we're going to drop 8 volts across the first resistor. We could probably kind of draw that kind of like this, 8 volts across that one. And then we have 2 volts across the second resistor. And again, we end up with a value of 0, which is our ground or our 0 volt level of the circuit. Now, a couple of things to note here. You'll notice that the larger resistor here is basically dropping or taking more of the voltage away in the circuit. And that's a very important principle in Ohm's law. If these were exactly the same, we'd expect the voltage to be divided evenly between R1 and R2. But in this case, the smaller resistor is dropping less voltage. And as that resistance gets closer and closer to 0 ohms, it is dropping less and less of the voltage.